Good morning, everyone. It's 9, so we'll begin. Nothing really in way of announcements. Nothing. It's still got some time, but you've got a homework due on October 4th, so that's Thursday. So plenty of time. That's 4A. We'll have covered that material long before the actual homework is due. So the clicker question. Which of the following are insoluble in water? Now, I've got a comprehensive set of rules here, okay? But keep in mind that the ones you actually have to memorize are these solubility rules, okay? This set, okay? These are the official lists that you have to memorize. So for doing your sapling homework, other assignments, this table is included in your notes because you may get something like a sulfide that's not on the official list that you may have to reckon with. So this is a comprehensive list, something you don't have to memorize, but which everything in it. There's some overlap. But this list is the definitive one that you have to memorize to answer exam questions. Okay? So which of the following are insoluble in water? So I want to see what y'all thought. See what you thought. Okay. D, C, D, lots of different answers, but D. Okay, we'll just go through them one by one. Okay, the last class was a little bit rushed, but show you a process for what you can do for them. Okay, so one, look at the anion. And then ask, what's the general rule? So for this first one, hydroxide, okay, generally they're insoluble. Okay, if you look down on this list, so compounds containing are generally insoluble. Hydroxide and sulfides are as well. Okay, generally insoluble. Okay, generally. Okay, then two, look at the cation. Is an exception. Okay. Here, the 6 exceptions that you have to have on your radar that we will expect you to know: calcium, barium, strontium, CBS, and mercury, silver, and lead. The happy metals. Okay. Calcium is one of those 6 exceptions. Okay. So, and calcium, the CBS metals. Calcium, barium, and strontium, they're a little tricky because sometimes they render a compound soluble, sometimes they render it insoluble. Okay? It's the opposite of the general rule. Okay? So, calcium, okay, hydroxide, generally insoluble. However, when they pair with calcium, okay, they are the opposite. It is an exception. Okay? So 3. If exception, let's say, overturn the rule. Okay, so calcium is an exception. So, exception, calcium hydroxide is soluble. Okay, so it is soluble, so it's not A. Sodium phosphate, with any time you see a group 1 metal, sodium, lithium, potassium, they're always soluble. Okay? Soluble. Okay? Calcium sulfide. Again, sulfides are generally insoluble, but the same rule for sulfide applies for hydroxide. It is also soluble. Okay? Here, chlorides, normally soluble, however paired with mercury. It's the opposite rule. Mercury chloride, mercury 1 chloride, is insoluble. Okay. So you all were right if you answered just D. Most of you all did. Okay. But lithium fluoride, lithium to group 1 metal, no exceptions. It is soluble as well. Okay. Questions? So they can. It's this process is what I recommend. you got to look at the anion. You have to know the general rule. Cash and G is the one that you've got to commit to memory. Okay? Then look at the cation. Is it an exception? If it is, it's a double agent. It reverses the rule. Okay? Questions? Okay. You have to know this to do what we're going to discuss today, precipitation reactions. Right? And we'll actually do one in front of y'all here in a minute. Okay? But you have to know solubility rules, and you have to remember all your rules for naming and balancing ionic compounds. Okay? Chemistry's cumulative. You've got to know those things to do precipitation reactions. Okay? So precipitation reactions, what you need to recall ionic compounds. So both naming and charge balancing. Okay? So you have to recall solubility rules. And you have to recall balancing chemical equations. Okay? So it's a cumulative topic. You have to have a solid foundation for those three things in order to do precipitation reactions. Okay. Okay, so what is a precipitation reaction? Okay. Precipitation reactions result when two, I guess technically speaking, or more, but for our purposes, two, when two aqueous ionic compounds are mixed, forming a new insoluble ionic compound. Okay? That insoluble ionic compound is called a precipitate. So an insoluble compound that results when you mix two aqueous ionic compounds together is called a precipitate. And you'll see here in just a second why it's called that. It falls out of the solution. It falls out like you would precipitation from the sky. Okay, same idea. You'll get to see one momentarily. Okay? But so the reaction that I'm going to show you all, before I show it, I'm going to show you what it looks like on paper. So we have lead nitrate, lead 2 nitrate, aqueous. I'm going to combine it with potassium iodide, aqueous. Okay? So I know that those are aqueous. Nitrates are always soluble. You've got to know that solubility rule. Okay? Anything with a group 1 metal, potassium, they're always soluble. They're aqueous. When they mix, what I'm going to write underneath them is charges. Nitrate is -1. You've got to remember that from it's cumulative. Okay? I have 2 of them. By an audible response, what's the charge of lead? +2. Okay? During precipitation reactions and acid-base reactions, these charges do not change. It's going to be important for balancing the products. Okay? Potassium, +1 to group 1 metal. Iodine, -1. If you write 1 minus, that's fine too. Okay. So during the precipitation reaction, plus 1. Okay. The cation here will pair up with the anion, and vice versa. The cation here will pair up with the anion. They dance. Okay, it's hokey, but anyway, they switch partners. Okay. So you can draw that. Lead is going to pair up with iodine. Okay. Potassium is going to pair up with nitrate. Okay. And whether they're soluble or not is solubility rules. Right? So we'll do the lead iodide first. So PBI. Okay. +2 -1. The charges do not change. Okay? So the lead's still +2, the iodide's still -1. Is this ionic compound charge balanced? No. Okay? So you have to make sure that the ionic compound is written correctly. Okay? To balance it, what do I do? I give it 2 iodines. Okay? Okay? That's the correct charge balance. 2 times -1 is -2, +2, sum of those charges is 0. Okay? I know solubility rules. Okay? Iodine is a halogen, a halide. Normally they're soluble, but it's paired up with one of those happy metals. This is a solid. It will precipitate out of the solution. And then KNO3, potassium nitrate. Nitrates are always soluble. Potassium is always soluble. This will stay aqueous. Okay? So now, that equation, the ionic compounds are right, but the equation is not balanced. Okay? So that's the recall portion. Okay? So step 1, so charge, balance the products. You always do that first with precipitation reactions. Always. You have to do it first. Then step 2 is balance. Okay? So I've got lead, I've got nitrate. Okay? Nitrate stays together. I've got potassium, and I've got iodide. One lead, 2 nitrates, 1 potassium, 1 iodide. Okay. On the product side, 1 lead, 2 iodides, 1 potassium, 1 nitrate. Okay, so I'm not balanced. Okay. So to balance it, I'll start with the nitrates. 2 here, 1 here, there are 2. 2 potassiums. Come back over to the other side. The potassiums are out of whack. There are 2 there. 2, 2. I'm balanced. Okay. So that is the reaction. Charge balanced for the ionic equations, for the ionic compounds, and balanced chemically to make sure that I've got the same number of atoms on each side. Okay. Questions? Okay. Now, this is on paper. I'm going to show you what happens when you do a precipitation reaction. Okay. So I'm going to be a good chemist and put on goggles. And they're orange. Yeah. Okay. So now, this really is, never mind. No. Always wear goggles and gloves. Okay. This is a solution of potassium iodide. Notice it's clear. Hopefully y'all can see that. Even in the back, can y'all see this? Look up. Okay. It's clear. Okay. Potassium iodide is soluble in water. It's clear. Okay. Put it in a test tube. Oh no. The cap's off. Anyway, it's supposed to be clear. Now the cap's, oops, that's why I wear gloves. Okay. Potassium iodide is not dangerous, but hold on. Stumbling, fumbling chemist. Okay. There we go. There, a little better. Okay. I know the suspense is killing y'all. Okay. So clear. Okay, clear. That's the potassium iodide. This is the lead nitrate. Okay. It is clear. Okay. solubility rules. It's dissolved. Now I'm adding the two together according to that chemical equation that's on the screen. See what's happening? That yellow substance is the lead iodide. Okay? That is a precipitate. It fell out of the solution. Okay? Had two clear liquids, okay? Have a yellow precipitate. Okay? So it's better than magic. It's real, right? So that solid that formed was the precipitate. Okay? And then I'm not going to balance this equation, but I just like doing stuff like this. So see what happens. Mr. Woodrum, he's our demo person, and was kind enough to set this up for me. Again, this is the potassium iodide again. This is silver nitrate, another one of those happy metals, silver. This isn't going to be as dramatic, but okay. See the solid crashing out. Okay. It's not as pretty, not as bright yellow, but still a solid. It's kind of a grayish color. Okay. So that is a precipitation reaction. So you might ask, well, what is that used for? Why is that used for? Used to old lead-based paints, if you change the ligand, the anion, you could change the colors. So you could have insoluble ionic compounds emulsified in polymers to create paint of different colors. Okay? Oop, clean things up. Make a mess. Now, what you're probably thinking, well, I don't know if you're probably thinking this. I've got orange goggles, I have an orange calculator, and you're probably thinking, am I trying to do a Donald Trump chemist impersonation? The answer is no, but anyway, I just think that's, orange goggles, orange glasses, and then totally precipitated. Anyway, it's a bad joke. I know, it's hammy. But anyway, I couldn't resist. Oh, orange one. So. Okay. So, that is what goes on in a precipitation reaction. Okay. Balance your charges. Balance your charges for your ionic compounds. Balance your chemical equation. Know your solubility rules to predict the insoluble product, the precipitate. Okay. Moving on. So, what was written here is a complete chemical equation. Okay, it tells you it's balanced. It's a chemical equation. Okay. There are two additional types of equations that chemists are interested in. So before we write the net ionic equation for a reaction, step one is you have to write what's called a complete ionic equation. Okay. And I'll just show you what that is. Okay. It's a complete ionic equation. So we've got silver nitrate in ionic compound nomenclature rules. You have to be able to kind of get a formula from a name. We've got AgNO3, aqueous. Okay. That was what we had in the bottle there. Okay. So nitrates are always soluble, plus sodium chloride, that's NaCl. Again, you have a switching of the chemicals, plus one charge, minus one charge, plus one, minus one. Okay. Got to know those charges as well. Here, everything is the same charge, so it'll balance when we're done. Silver pairs with chloride, solid. The sodium will pair with nitrate. and it's aqueous. Okay? And you have to know the solubility rules. So this is the chemical equation. Here, modify that. So this is the chemical equation. Okay. And then 2, the complete ionic equation. Okay. Shows each ion separated and aqueous. Okay. The precipitate stays together. Okay, that key point. Okay. So taking this equation, how it's written as a complete ionic equation, it's in the name, write them out as ions. You've got silver, okay, separated from its compound, so aqueous, silver aqueous, plus nitrate minus aqueous, plus sodium aqueous, plus chloride aqueous. Okay? So you've got all of your reactants spaced out, well, not spaced out and not paying attention, but anyway, spaced out in being ionic, okay, being dissolved. Okay. So that's the reactant side. Okay. I'm just, for room's sake, I'm going to come over here and indent, so to speak. Silver chloride is a solid. It stays a solid. Okay. It does not exist as being dissolved. It stays together. Okay. Plus sodium aqueous plus nitrate aqueous. Okay. So that is a complete ionic equation. Okay. It shows everything that would be in the solution that is an ion, and then the solid that forms stays together. Okay. So the complete ionic equation. Next. 3. The net ionic equation. What that means is you cancel the spectator ions. So that key term. Okay. Spectator ions are just that. A spectator for a spectator sport is the spectators just sit and watch. Okay. They're not doing anything. They're not precipitating or participating in the reaction, right? So the spectators, when we refer back to the complete ionic equation, are sodium and chloride. Oh, not chloride, sorry. My bad. Nitrate. Spectator. The reason they're called spectators is they're not changing. The sodium is still sodium. It's still aqueous. Okay? It's in the solution, but it's not doing anything. It's just there. Okay? The nitrate, the same. Okay? Okay. So the net ionic equation shows actual change. So to write that, the net ionic equation was you have silver, aqueous, combining with aqueous chloride to make silver chloride solid. That is the net ionic equation. Okay. The spectators are not included. Yes, question. They do. So the question was, does sodium nitrate make an ionic bond, or do they form it? They stay aqueous. Okay, they will not. So an insoluble ionic compound, that's precipitate. When we learn about electronegativity, it's a measure of how hungry an atom is for electrons. Okay, depending on the differences in electronegativities between atoms, that bond, a silver chloride bond, is actually kind of covalent. Okay, but we're not there yet. We're not at that point. So silver chloride is covalent in its nature a little bit, and they stay together. That covalent bond will not be separated by water. Okay, but yes, sodium and nitrate separate, and they stay separated. Other questions? Okay, that's the process. Okay, so start with a balanced chemical equation, a complete ionic equation, identify your spectators, cancel them, and then write the net ionic equation. Okay. If you want to use an analogy, this is your take-home pay. This is what you get after taxes. What this is what you get before taxes, if you want to use that analogy. Okay. Questions? Okay. So what I'm going to ask you all to do, okay, I've done a lot of talking, a lot of demonstration, is I want you to work through this problem, and when you're done, write the net ionic equation, okay, and make sure you include phases. Okay, I'm going to walk around and see you all working on this. Okay, it's already balanced. I've given you the balanced chemical equation. But write the complete ionic equation, and then when you're done, as far as the reef input, write the net ionic equation and include the phases. As a hint, remember that subscript, recall from class on Wednesday, becomes a molar coefficient. Okay, if you write K2, that implies that you've got a diatomic potassium. Okay, when it dissolves, it's potassium ions. Okay, so that 2 does not stay there whenever you dissolve an ionic compound. The 2 becomes a molar coefficient. Okay, so remember that from class on Wednesday. K2 implies that you have diatomic potassium. Diatomic potassium in solution does not exist. It's potassium cations dissolved. to, okay, as I've walked around, okay, a common mistake I've been seeing, okay, let's look at it. If we just look at the potassium sulfate, okay, if we just look at that one, so we've got K2SO4 aqueous. Okay. That dissolved, a way that you can think about it may help, is that will dissolve into 3 ions. Okay. You might ask, why 3? You have to recognize that sulfate is a polyatomic ion. The S, the sulfur, and the oxygen, those stay together. Okay? So you get 2 potassium cations and 1 sulfate anion. Okay? And that dissolves. So it will dissolve. The 2 comes up front. So 2 moles of potassium cations and 1 mole of a sulfate anion. Okay? So when you look at these, a kind of a way to maybe help is there are 3 moles of particles, of ions in this. 2 potassiums, 1 sulfate. 2 potassiums, 1 sulfate. Okay? Here, well, that's the precipitate. That doesn't help. So anyway, but that is the correct way to show potassium sulfate dissolved in water. Okay? So the 2 is not a molecular compound that is composed of 2 potassium cations. That's how that dissolves in water. Okay. Questions? It's a tough. This is generally a tough topic because there's many moving parts in it. Also, if you're to enter it in reef, just use a greater than symbol for the reaction arrow. Okay, you might have wondered what to do there, so greater than, something like that. So greater than. Okay, you can use that. Okay. I've walked around, and I think people are arriving at an answer. So guidelines, some questions that I've gotten. On the reactant side, the reactants are always aqueous. Okay? So you always have to split the reactants into cations and anions. Okay? Always, right? But so this dissolved. Okay? You've got that 2 comes up. So 2 moles of potassium cations plus 1 mole of a sulfate anion. Okay, that component. Now, you got to include charges. Another thing as I walked around, your chemicals balanced, but you have to show the charges of your ions too. So if you didn't do that, make sure you include it. Right? Okay, 2 moles of silver. Plus 2 moles of nitrate. Okay. So that 2, you've got to consider those in the balanced chemical equation as well. Okay. So that's the reactants. Okay. The products, we've got 2 moles of potassium, aqueous, again that 2 that's there, 2 moles of nitrate. Okay, I'm just running out of room. And then the solid is the silver sulfate. Okay. Ag2SO4. Solid. Okay. That stays intact. Okay. Okay. Solid here, solid there. Okay. That process. And then the spectators are potassium. Go through and cancel those out like you would cancel out like terms in a mathematical equation. Okay. And then the nitrate are the spectators. Okay. So the net ionic equation. Sulfate, aqueous, will react with 2 moles of aqueous silver to produce silver sulfate. Keep wanting to say silver sulfur or silver sulfur, but anyway, sulfate. Solid. That's the net ionic equation. Two moles of silver, 2 moles of silver, 1 mole of sulfate, 1 mole of sulfate. Questions? Okay. Those are admittedly tough. Can be. There's a lot of pieces you got to keep together. Okay. Next, just introduce the topic. Acid-base reactions, again, things that you have to recall or know, so general things. So the list of strong acids, okay, things to memorize. So you have to recognize that when you see HNO3, aqueous, HClO3 aqueous, H2SO4 aqueous, H3PO4 aqueous. Okay. So what these are, okay, are strong acids. They donate H plus in solution. So Arrhenius acid is something that donates or generates H plus. Okay, in solution. They, even though you would look at these and say, well, these are molecular compounds, there are no metals in them. Okay, but acids, or excuse me, strong acids, behave like soluble ionic compounds. Okay? They're a different category. Okay? They're not ionic in the sense of metal, non-metal, but they behave like an ionic compound. You get, so for example, if we had H2SO4, when it's dissolved in water, will yield 2 moles of protons. So H plus is called a proton, plus 1 mole of sulfate. Okay? As an example. Okay? So it behaves like an ionic compound. Okay? So list of strong acids in the list. Okay. Again, things to memorize. I didn't include all of them, but you have to recognize these are the strong acids. Strong bases. Okay? So hydroxide, sodium hydroxide, calcium hydroxide, and so on. Okay? They donate or generate hydroxide according to the Arrhenius definition. You'll learn about more acid definitions as you go on, but for general chemistry, they donate OH minus. They dissolve and behave like ionic compounds. Well, they are. There's a metal and a non-metal, and polyatomic ions. Okay. But for example, if you had calcium hydroxide dissolved in water, she wrote aqueous there, you would get calcium 2 plus, aqueous, plus 2 moles of hydroxide, aqueous. Okay. So hydroxide and a proton. Okay? So that list, that introduction. They behave like ionic, soluble ionic compounds. Okay? And then lastly, the products of an acid-base reaction. One is water. 2 is a salt. What that is a soluble, well, sometimes they're not soluble. We'll just say an ionic compound. Okay? Those are the products for every acid-base reaction according to the Arrhenius definition. Water results when you have protons combining with hydroxide to make water. Okay? Make water. Okay. Okay. So with that, we'll pick up here on Monday. Hope you all have a good weekend.